When you're in a small boat and the weather's bad, the sight of land can be a relief. But it can also be a danger. Coastal waters can be shallow and treacherous. The captain needs to know exactly where he is in relation to the land. This is the Anvil Point Lighthouse. It's a warning of rocks in the sea, and it's also a fixed point to be used for a compass bearing.
297!
297. Right.
The boat's navigator works from a chart of local waters. She draws a line from the lighthouse at an angle of 297 degrees to magnetic north.
$250.
2 more readings are taken on different fixed objects, and 2 more lines are drawn. They should meet at a point, but in fact they don't. On this occasion, as on most others, the 3 lines form a triangle, known to sailors as the cocked hat. Why do we get this so-called cocked hat? Why don't the 3 bearing lines meet at a point? The reason is that there are errors in the measurements. All measurements are subject to some error, and if each compass reading is a few degrees out, then the lines drawn by the navigator will miss the true position and form this triangle instead. So the question the navigator will ask is this: what is the relationship between the triangle and the true position of the boat? Now, the traditional belief of navigators is that the true position of the boat will be somewhere inside the triangle. Is this necessarily true? What we're going to do in this program is to try to answer this question using some of the ideas of probability and statistics that you've met in the course. To start with, we'll need to look in a little more detail at the measurements that are taken and get some idea of what sort of errors are likely.
This is a compass which might be used on board a small boat. It's called a hand-bearing compass, and it's designed to give as accurate a reading as possible. Inside the compass there are 2 small bar magnets mounted on a freely pivoting disc. The disc is graduated in degrees, and there's a small prism mounted above it which enables the graduations to be seen when looking across the top of the compass, like this. The bearing is found very easily by just noting which graduation is visible immediately below the object in question. As you can see, this compass seems capable of giving a reading accurate to within a degree. But of course that's with both feet firmly planted on the ground. Life's rather different on a rocking boat.
To see what errors we're likely to get with this compass, we decided to anchor by a buoy in the mouth of Poole Harbour. What I'm going to do now is take several bearings on fixed objects that I can see, like those tall chimneys. Since I know where I am, by the buoy, and I also know where those chimneys are, I can use a chart to find the true bearing. Then I can compare the true bearing with the bearing I've measured using the compass. So first I'll take a bearing on those chimneys. I'd say that was about 331 degrees. Of course, I'll need to take bearings on several more objects, but first I'll compare my bearing on the chimneys with the chart. What I'll have to remember is that it's a bearing relative to magnetic north rather than true north. At the moment, the difference between magnetic and true north is about 7 degrees, so I'll have to subtract 7 degrees to get my corrected measured bearing. That's 324 degrees. Now let's compare that with the chart. Here's Poole Harbour. Here's the buoy where we've anchored. The chimney I was looking at is over here. I'll measure its true bearing. It's 320 degrees. And now I can calculate the error. It's 324 degrees minus 320 degrees, which is 4 degrees.
I took several more bearings on other prominent objects and compared the compass readings with the true position on the chart, reading to an accuracy of 1 degree. This histogram shows the results. Quite a few of the readings had no error at all, but in general there were errors of a few degrees, up to 4 degrees in one direction and 6 degrees in the other. I took 16 measurements in all, and when I worked out the sample mean and the sample variance, these were the figures I obtained. The sample mean was minus 0.56 and the sample variance was 7.44. In fact, many thousands of readings have been taken using this type of compass, and it's known that when used in fairly rough conditions, the errors involved have mean 0 and variance 8.2. These results that we obtained are typical of those we might expect from a sample of 16 observations. So that gives us an idea of the error in each angle measurement. But really we're not interested in the angles as such. We're interested in the effect of the angular errors when we plot the position of a boat on the chart. Now at first sight this is a rather more complicated problem. For a start, it's a problem in 2 dimensions. So rather than looking at this problem straight away, we'll look at a rather simpler version of the problem, which occurs in particular circumstances. Sometimes you can find 2 landmarks which are in almost the same direction. In the foreground is a buoy which is marked on the chart. Further away is a prominent land formation called Handfast Point. As the boat sails along, the relative positions of these 2 landmarks will change. There will be one particular moment when a transit occurs. That is, when the buoy is directly in front of the land formation. When that transit happens, we know that the boat must be in line with the 2 landmarks. There won't be any question of a compass error.
So a transit simplifies the problem considerably. It means that we know that the position of the boat is somewhere on a fixed line. In this case, the line through the rock and the buoy. To find the position of the boat on this line, we just take one compass bearing on a different landmark, for example this castle. If we measure the bearing accurately, we should then get the boat's actual position, here. But the bearing is subject to error, and we shall actually estimate that its position is here, a distance y from the true position. We are interested in the size of this error along the fixed line. In the unit, we introduced a technique which can be applied in these circumstances. It is a method of finding the approximate mean and variance of a random variable y, which is a known function of another random variable x, when the variance of x is small. If y is equal to phi of x, then the variance of y is given by this formula, which relates the variance of y to the variance of x. Now we can use this formula to calculate a numerical value for the variance of y. We shall choose x to be the observed angle between the 2 lines. X is close to the true angle alpha, which we don't know, and as we've already seen, x will have mean alpha degrees and variance 8.2 degrees squared. We'll let d be the true distance of the boat from the castle. Then we can find the function relating y and x by applying a trigonometrical formula called the sine rule to this triangle. This gives y over sine x minus alpha is equal to d over sine x. And we can use this relationship to find the variance of y. And this is what we get. The variance of y is approximately equal to the variance of x times pi d over 180 sine alpha all squared. Now this formula contains d and alpha, neither of which we know. However, since the error is small, we can approximate to d by measuring the length of the line we've drawn on the chart. And we can approximate alpha by using x, the measured angle. In our case, we've found these values. D is about 1.05 kilometers and alpha is about 74 degrees. If we substitute these values in the formula, we get that the variance of a y is about 0.003 kilometers squared, and so its standard deviation is about 0.05 kilometers, that is 50 meters.
So we've found an approximate value for the standard deviation of the error. But there are other questions we could ask about this problem. For instance, what's a 95% confidence interval for the true position of the boat, given our measurement? How could we construct a range of plausible positions along the transit line when all we know is the measured position and the typical behaviour of the compass? Now what we've done so far is to find the variance of the error along the transit line, when what we know is the variance of the error in the angle. For a confidence interval, we need slightly more information than that. We need to know not just the variance of the error in the distance, but the way the error is distributed. And we can find that if we know the way the errors in the angle are distributed. So what we need to do is go back to the data we collected about compass errors. Here's the histogram we looked at before. Can we try to fit a probability distribution to this histogram? Now there's a lot of evidence which suggests that certain types of measurement errors are normally distributed. If we just make a visual comparison between a normal curve and the histogram, then it's difficult to see whether the fit is any good, because the data set is quite small. But of course you've met statistical techniques for checking the goodness of fit, and if you use those techniques, you'll find that the normal distribution is reasonable for the data we have collected. And in fact, experience has shown that the errors involved in using this type of compass are indeed approximately normally distributed. So we'll say that x minus alpha, the random variable representing the error in the angle, is normally distributed with mean 0 and variance 8.2. And this can be used to find the distribution of the distance error along the transit line. This is the relationship we had before between y and the angle error x minus alpha. Now it can be shown that if the angle errors are normally distributed, then so, approximately, are the distance errors. So y is approximately normally distributed with mean 0, since the angle errors have mean 0, and we've just seen that the variance is about 0.003. And now we can calculate the confidence interval. For a normal distribution, we construct a 95% confidence interval for the true position by first making an estimate of that position and then making the interval extend 1.96 standard deviations on either side of the estimate. So the confidence interval will be the measured position plus or minus 1.96 times the square root of the variance. And if we do the calculation, the interval turns out to be from minus 0.1 to plus 0.1. Now let's look at that on the chart. What we've found is a 95% confidence interval for the error along the transit line. We're 95% confident of being within this 200-metre interval. And we interpret this by saying that on 95% of the occasions when we use this procedure, the interval we get will contain the true position of the boat. The navigator on the boat might be satisfied with that. But of course this is a rather specialised situation. It involves a transit between two fixed points to get a known line. What happens if the navigator isn't so fortunate?
If the navigator can't find a convenient transit, then usually the only possibility will be to take bearings on fixed points like this. Of course, one bearing won't be sufficient. At least two will be needed, and the standard procedure is to take 3. Before we look at that, we shall consider the case with 2 bearings. Let's suppose that the true position of the boat is here, then this is the true bearing line. But there will be an error in measuring the bearing, so when the line is drawn on the chart, it will be incorrect. We shall call the error in the first angle x1. Similarly, for the second bearing, this is the true line, and this is the line drawn on the chart, with error x2. These two lines from the observations taken meet here, and this is where the navigator guesses the boat is. In general, the estimated position of the boat is different from the true position. In the previous case, the transit, we knew the boat's position was on a fixed line, so we had a one-dimensional problem. But here we don't know that, and there are two dimensions to the error. We can think of the error as having two components, an east-west one, y1, and a north-south error, y2. y1 and y2 are both functions of x1 and x2. So now we have two random variables to represent the error in the position of the boat, and they will have a bivariate probability distribution. This makes the problem more complicated than the simplified case we looked at earlier with a transit. Because of this, we are not going to show you the mathematics, but just try to give you a feel for what is happening. We've made a surface which represents the bivariate distribution of y1 and y2. These are the two landmarks we used for the bearings, and this surface represents the probability density function of the estimated position of the boat. The maximum value is here, the true position of the boat. To help you get a feel for the distribution, we've drawn some contours on the surface. These contours join points which have the same value of the PDF. Also, the total volume under the surface is equal to 1, and the volume under any particular region is equal to the probability that the estimated position of the boat is in that region. The probability that it's in this central region is 1/10. The probability that it's in this next ring is also 1/10, and so on. So the probability that the estimated position is within this main hump, bounded by this contour, is 9/10. This gives us a picture of the observed position of the boat in terms of probability, when we know the true position. In reality, of course, the navigator knows the observed position, but doesn't know the true position. What she would like is something analogous to a confidence interval, though for this problem it will not be an interval, but a region. Given the measured position of the boat, we might devise a procedure to construct a 95% confidence region. That is, a procedure which gives us regions, 95% of which will contain the true position of the boat. Now, confidence regions are much more complicated than confidence intervals. For a start, there's the question of what shape of region is appropriate. We might choose a square region, or perhaps an elliptical region, because these contours are approximately elliptical. And then, having chosen the type of region, we'd have to try and calculate it. As you can imagine, it would be a formidable task. However, this is the situation for just two bearings. As we said at the beginning of the program, the standard procedure is to use 3 landmarks.
We didn't find a confidence region for the case of 2 bearings because the procedure was too complicated. But it turns out that for 3 bearings there's a confidence region that appears naturally, the cocked hat triangle. If these are the 3 true bearing lines, then the 3 measured lines could be like this. The measured lines are subject to a random error, and in this case the triangle does contain the true position of the boat. But because the error is random, if we draw the lines again, we might get a triangle that doesn't contain the true position, like this one. So this is a random triangle, and we can ask what is the probability that such a triangle contains the true position. If, in the long term, 90% of such triangles contain the true position, then we'll call the triangle a 90% confidence region. That's just like we defined a confidence interval in one dimension, except that here we have a triangular-shaped region instead of an interval. So what is the probability of the triangle containing the point? In fact, it's not too difficult to calculate that probability, but before we do that, we'll get an idea of its rough value by performing some simulations. Here's the true position, and here are 3 random lines where the angular error has the same distribution as the errors we found for the compass. This triangle doesn't contain the true position. Let's continue with 100 simulations. The computer will indicate when the triangle contains the true position. Now you may have thought that not many of those triangles contained the true point, and in fact you'd be right. Only 28 out of the 100 did so. And you might find this surprising because according to sailing tradition, the triangle should contain the true position most of the time. So is this low result a feature of the particular configuration of points we've chosen, or of the particular distribution of errors? In fact, it isn't, and I can demonstrate using this diagram that the probability that the triangle contains the true position is only 1/4, and that's always true, no matter what the distribution of errors or the layout of the points. This is how the argument goes. Let's start with the middle bearing of the three. The error in this bearing could be clockwise or anti-clockwise. Let's suppose for the moment that it's clockwise. Now let's look at the other two errors. Can they be clockwise too? If this error is clockwise, then the triangle certainly won't contain the point. And if the third error is clockwise, then again the triangle won't contain the point. But if both the other errors are anti-clockwise, then the triangle will contain the point. So, when the middle error is clockwise, out of the 4 possible cases for the other two errors, only one gives a triangle containing the true position. And what about when the middle error is anti-clockwise? In that case, the triangle will only contain the point when the other two errors are clockwise. Again, 1 case in 4. So combining these results, out of the 8 possible cases, only 2 give a triangle containing the true position. And if we just know that a clockwise error is equally as likely as an anti-clockwise error, then the way the errors are distributed doesn't matter. All the 8 cases are equally likely, so the probability that the triangle contains the true position is 2/8, 1/4. And whatever the arrangement of landmarks and boat position that you choose, you'll still get the same answer, 1/4. So now we have an answer to our original problem about the cocked hat triangle. And surprisingly, it's a much simpler answer than we might have imagined. But as far as a navigator is concerned, it's a disappointing answer. The cocked hat was supposed to give a good indication of the location of the boat. But as we've seen, it's really only a 25% confidence region. 75% of the time, it'll be wrong. So there's only one message we can give to navigators using this system. Watch out, it's not as accurate as you think.